So we're going to talk about a couple of state changes. Sublimation is the change from a solid directly to a gas. And this seems a little unnatural because usually things melt into a liquid before they turn into a gas. But many things actually can sublimate. And so that's a term you should understand, you should know. Sublimation is going from a solid to a gas. The opposite of that is called deposition. And so that's going from a gas directly to a solid. So here we have an illustration of a block of ice. We have our water molecules here, and they're all vibrating. They have a certain amount of kinetic energy due to the temperature, the thermal energy. It's an average kinetic energy, so some of them are higher in energy and some are lower. And so if you have higher energy molecules that are at the surface, they can just break off into the gas state without the whole thing melting. And so this, for water, this can happen well below the freezing point. The water molecules will just break off and go into the air. So as a result of that, solids can also have a vapor pressure. It's usually much lower than liquids, but they can have it. So sublimation will usually happen faster in an open container, because then when those molecules sublimate, then they're going to go away, right? If it's in a closed container, there's a better chance that they'll actually bounce around and get stuck again and not end up leaving. But sublimation can explain some things that we see in the freezer at home. Ice cubes left in the freezer slowly shrink. Have you ever found some ice cubes in the back of the freezer and they're a lot smaller than the rest of the ice cubes? Anybody see that? Or stuck in the ice maker? Yeah, they get smaller. Why? They sublimate. Okay, so there's ice there. They're not melting. There's just molecules leaving into the gas state. Seems kind of crazy. Ice crystals grow inside airtight bags of frozen foods. So you got the tater tots that you found in the back of the freezer, and you're like, why did I buy these? But I don't have any food left, and so I'm going to finally eat these, right? So you open the bag and you dump them on the pan, and there's all this snow in the bag, right? All these ice crystals. And you're like, what the heck? That's going to make them all soggy. Now we have to sort this out. It's just not good. Where does that come from? That water in the snow is water that used to be in the tater tots, because potatoes have water in them, right? And so in the freezer, the water sublimates, goes into the gas state, but because it's in an airtight bag, it can't actually leave the bag, but it doesn't end up back where it started from. It ends up forming all these ice crystals around in the bag. Sublimation also explains freezer burn, where foods that have been in the freezer for a long time can get dried and gross on the outside. It's called freezer burn. Not exactly sure why. So how can you avoid some of these things? If you have a deep freeze, which has a much lower temperature than a regular freezer, sublimation will happen at a lower rate. For the rest of us, we can stop some of this by sealing the food without any airspace. So if you use a vacuum sealer, or you very carefully, wrap it in foil and then put it in plastic and squeeze out all the air, sublimation will still occur, but the water molecules can't really go anywhere because there's no space for them to go. So they'll leave and they end up coming right back. So that can help preserve your food. Does anybody have any questions about that? That's kind of practical. So, you've heard of dry ice, right? You know why they call it dry ice? Because it doesn't melt. Yeah, so regular ice, I guess, would be wet ice, right? So you put regular ice in your cooler and you've got your sandwiches on top, and then you get to the picnic and the ice has melted and all your sandwiches are soggy and gross, right? Because they were in plastic, but somehow there was some hole and the water found its way in. Dry ice is solid carbon dioxide, and it does not melt. it just sublimates. And so here's a picture of some dry ice. And what we're seeing here, it looks like there's like this vapor or something streaming away from it. That's actually the cold carbon dioxide gas moving away. And it's so cold that it's causing moisture in the air to condense. And that's why you can see it, is you're seeing this little cloud formed by the coldness. So it sublimes at room temperature but doesn't melt. And so this is used, like, if you're shipping a drug that needs to be refrigerated or refrigerated foods, putting dry ice in there will keep them cold, and you don't have to worry about water leaking all over the place, because people who ship packages really don't like it when liquids leak out of the packages. It's kind of scary for them. Another state change is called fusion. So most people call this melting. So melting and fusion mean the same thing. That's going from a solid to a liquid. The opposite of that is called freezing, going from a liquid to a solid. I used to have a hard time remembering what fusion meant, and what helped me was to think about, you put a bunch of chocolate chips in a saucepan and you stick it on the stove and you heat it up slowly. And as the chocolate chips melt, they fuse together, right? And if you let them cool down again, it's just fused. It's all one thing now. So if that helps you, great. So as we heat a block of ice, the molecules are going to vibrate faster. And when you get to the melting point, the molecules have enough energy that they can slide around. So they're not like breaking free, but they're breaking loose enough that they can slide around next to each other and become a liquid. So this is one of those heating curves. Here at -10, we've got ice, and as we add heat, the ice will increase in temperature until it gets to the freezing point, the melting point, 0 degrees Celsius. At that point, just like when we were boiling water, the temperature is going to stay the same until all the ice has melted, because the heat that you're putting in there just causes more rapid melting. The temperature cannot go above 0 until all the ice has melted. This makes 0 degrees Celsius a really convenient temperature, because you don't even need a thermometer. You don't need any special equipment. All you need is a bucket of water with some ice. And okay, there you go, that's 0 degrees Celsius. And say you have a reaction that you want to occur at 0 degrees Celsius. You put the flask inside the ice water, and you know what temperature it is. Once all the ice has melted, then the liquid water temperature will increase. Any questions? So melting is an endothermic process. This one usually makes sense to us, because how do you get something to melt? You heat it up, right? You put heat into it. Heat of fusion is the heat required to melt 1 mole of a solid. So we talked about the heat of vaporization, the heat required to vaporize 1 mole of a liquid. This is melting a mole of solid. So going from 1 mole of solid water to 1 mole of liquid water requires 6.02 kilojoules of energy. What is not as obvious is that freezing is exothermic. Usually when we think of an exothermic process like, combustion, we're like, it's giving off heat, right? It feels hot. How is freezing exothermic? Well, it's the opposite of melting, so it has to be. But how do you freeze water? Well, you stick it in the freezer, right? What does the freezer do? The freezer is pulling heat energy out of the inside of that box. So at room temperature, freezing is not a spontaneous situation. It's not just going to happen on its own. You have to actually pull the heat out of it and get it to a lower temperature before it will freeze. So this is a phenomenon that's used to protect citrus in the winter. So we're just getting to that point now. I live in Reedley, and there's orange groves and stuff all over the place. And the oranges are picked in the winter and early spring, and so if you get a bad freeze, it can take out your entire orange crop. So because of, well, never mind, I'll not go there. So how do you keep the oranges from freezing when it gets below freezing, below 32 degrees Fahrenheit? Well, a rather effective way is to water the fields. So you put a lot of water out there, and what happens as the air temperature goes down, that water will begin to freeze. But remember this heating curve? We're going the other way now. The temperature's going down. Once the water starts freezing, it's going to remain at the same temperature until all of it has frozen. So as it's doing that, it's releasing heat into the surrounding air to keep it at 32 degrees Fahrenheit. Turns out oranges don't freeze until like around 26 degrees Fahrenheit, and it takes a couple hours for that to happen. So if you can just keep the temperature just a smidge higher, you can protect the orange crop. And then a lot of times they'll use the fans as well to take that warmer air from the bottom and blow it up around the fruit that's higher up on the tree. Anybody have any questions about that? So the heat of fusion is usually a lot less than the heat of vaporization. You can see that in this graph. So here's water, there's the heat of fusion, and here's the heat of vaporization. Heat of vaporization is much greater because you need to take those liquid molecules and break them completely free from the other molecules. Whereas to go from a solid to a liquid, you just have to be able to slide from one molecule's stickiness to another molecule's stickiness. You don't actually have to completely break the intermolecular forces. You just need to partially overcome them.